We have a couple other common effects that lead to the line widths being broader than just strictly what the natural line width would be for a transition. The first that we're going to talk about is what's called Doppler broadening. And this is based on the Doppler effect. And you're familiar with the Doppler effect. You've probably heard the Doppler effect in terms of sound. If you have something moving towards you, the frequency at which you observe or hear the sound, or this applies to light as well as sound, which is why this matters for this, the frequency at which you hear it. So if you say if there's a train coming towards you, the sound will be higher pitched than when it's moving away from you. And then the sound will be lower pitched. You've probably heard this, like when something goes past you, right? It starts high pitch, goes to lower pitch. And that's the frequency of the sound that you're hearing. The same thing applies to atoms or molecules. The Doppler broadening also applies to molecules just as much as it applies to atoms. So if you have an atom here, this is represented here, and you have a wave of light coming towards it, if the atom is moving towards the, right, if the light and the atom are moving closer to each other, this leads to an effective, the increase frequency that's observed by the atom. Whereas if it's moving away from it, the effective frequency is decreased. What this means is that in a sample of atoms that's in a flame or just in a furnace or whatever, you'll have some mixture of atoms moving towards and moving away from your light source. So if we consider, right, the normal, right, the natural broadening looks something like this. Some of the atoms in our sample are moving towards, all right, so this is our frequency on the bottom here. For the atoms that are moving towards the light, right, so things from up here, they're going to show up a little bit higher frequency than this. And these ones that are moving away are going to show up a little bit lower frequency in this. And so overall, that leads to a line that is broader. Oh, it moved in the middle, okay, than the natural line width that we showed here. And this is the main thing that affects Doppler broadening is temperature. This is essentially a temperature effect because that affects the speed at which these molecules are moving relative to the light source. And so we can quantify Doppler broadening. Our delta lambda, right, our change in our line width in terms of wavelength is approximately equal to lambda, the wavelength we're measuring at. We've lumped a bunch of constants together here, 7 times 10 to the minus 7, divided by the square root, or times the square root of t divided by m. And that should be capital M. All right, now T here is temperature in Kelvin. And so we can see this directly depends on temperature. The higher the temperature, the broader the lines will be. And big M is the, in this case, we're talking about atoms, so the atomic mass in Daltons. Specifically for this equation here. You can express the atomic mass in different units, but then this constant, the 7 times 10 to the minus 7, will change. And so the mass of the atoms also matters for this, but that's not something that will change from experiment to experiment. The temperature is what's going to change. So let's look at what, so we know the approximate line widths for natural broadening. Let's see what we get if we, again, look at our sodium again. Look at the same transition we've been looking as our example. Delta lambda is equal to 589.756, which is our wavelength, times our 7 times 10 to the minus 7, times the square root of, let's do a flame here, 2500 Kelvin. We could do this for ICP as well, divided by 23 Dalton. Right, so that's the atomic mass of sodium. All right, and that gives us a line width of 0.0043 nanometers. All right, and so this is about 10 times bigger than the natural line width, than the lifetime broadening. So again, this is going to lead to a bigger line width than we get from just if the atom was at low temperature. We have one other source of broadening that's called pressure broadening. And as you might expect, this depends on the pressure of our sample. So Doppler broadening is essentially, for a given atom, it's a temperature effect, though it's also a mass effect, because that affects the speed of how fast things are moving. For pressure broadening, on the other hand, this is depends on collisions between atoms. Atoms and whatever else your sample is in. Collisions between atoms can cause relaxation to the ground state, and effectively that decreases the lifetime. We can say that decreases dt, the lifetime, and the number of collisions you get depends on the pressure. So the effect of this is similar to Doppler broadening. There's no clean equation for this, unlike Doppler broadening, but the effect of this d lambda is about 10 to the minus 3 to 10 to the minus 2 nanometers for something in the visible range. And so this depends on pressure, right? You'll have more collisions the higher the pressure is. So the higher the pressure, the broader the lines will get. The lower the pressure, the less lines will get. Again, this is not specific to atoms. This happens with molecules as well, but this is particularly relevant for atomic spectroscopy as well. Okay, so now that we know about all these sources of broadening, in the next video we're finally going to talk about hollow cathode lamps and why they work the way they do, and why they allow us to get light that is narrower than the absorption features we're trying to measure, which lets us use Beer's law.